Welcome to the first Software and Computing Roundtable of 2021. Today, we follow up on the discussions of the workshop which we had, Future Trends in Nuclear Physics Computing, where we discuss about the community. And today we will follow up on community organizations in high energy physics and nuclear physics. We will start the presentation by an in-depth introduction to our new partner in the Software Computing Roundtable, the HEP Software Foundation. And our first speaker today will be Graeme Stewart from CERN, who will give us an overview about the work the HEP Software Foundation is doing.
Okay, so great. So it's a pleasure to join you here again for the roundtable, but this time on the presentation side, and to tell you a bit about the HEP Software Foundation, and to give you, well, a pretty quick tour of what we've been doing inside of the HSF, and also some of what we're planning to do in the next years. So first of all, let me start, of course, just by a bit of motivation of why the HSF exists at all. And I think, the primary driver, of course, is the science program that we have in physics. And this is a very ambitious program which foresees a lot of upgrades over the coming decades. They actually start extremely soon, because with LHC Run 3, we actually have pretty much new detectors in ALICE and LHCb, and much higher readout rates from both of those detectors. So that's their big upgrade. And then in about 5 or 6 years' time, we will have the high luminosity LHC, particular for ATLAS and CMS, which will again renovate their detectors so that they're almost new, particularly the inner detector components, and also increase the trigger rate by about a factor of 10. So a huge increase in both data rate and data complexity, because the instantaneous luminosity will go up as well. So this obviously brings an enormous challenge in terms of software and computing. So that's what's happening at the LHC. But then, of course, outside of the LHC, we have Bell2 now taking data. We have June, which is being planned on a roughly similar timescale to high luminosity LHC. Of course, we see on the horizon the EIC and FAIR in Europe as being next generation nuclear physics experiments. And not only that, of course, we've already started to discuss what the next generation of accelerators might be as well, with options including an ILC, an FCC, probably an FCC-EE at CERN, or even the Chinese proposal for the CEP. So there's a lot which is coming up in terms of high energy. And just as a quick reminder, we already, of course, as a field, have a vast investment in software, and probably about 50 million lines of C++ in total being actively used in the community, which would cost an enormous amount if we asked industry to develop it for us. Of course, it's critical for all of our physics, from triggering all the way through to the final plots that we make. And the LHC experiments are about the scale of using 1 million CPU cores basically every hour of every day. We have about an exabyte of data already, and roughly 100 petabytes of data transfers per year. So we're really at the huge scale in terms of science. This is a huge and ongoing cost, and of course we have all of these challenges ahead to support the physics program to come, not just the physics program that we have today. Meanwhile, of course, we have technology evolution, and this won't be anyone, I think, in this audience, is that Moore's law is continuing to deliver increases in transistor density, although it's clear that the doubling time is lengthening. Meanwhile, clock speed scaling failed quite some time ago, so really processors can't get any faster in terms of their clock speed, as lead currents become the important source of power consumption, even as you shrink the transistor size. So we're essentially stuck at 3 gigahertz clocks from the underlying power wall limit. And another thing which is terribly important if you want to have efficient software is to pay attention to memory access times. So data layouts become more and more important for effective software and computing. This sort of evolution was nicely summarized in an ACM paper, I think from maybe 2 years ago now, but I think that the conclusion that it has is still very relevant, where you can see that we moved from this green golden era of risk computing, where the year-on-year improvements were really very large, to a multi-core era, to an era where throughput is dominated by Amdahl's law, and then they predict some end of the line for the next coming years until we perhaps even hit physical limits of transistor size. So of course it's not all doom and gloom. I mean, there are even some promising new CPU architectures now. People are probably aware of the Fugaku supercomputer in Japan, which is the current #1 based on the ARM A64FX. Apple's new chips made quite a big splash, and actually even for the venerable old x86, the new AMD chips are performing on a rather better improvement rate than we're currently getting from Intel. One thing that drives all of this actually is computational power efficiency, and that goes from your mobile phone, in fact, all the way through to HPCs. So the conclusion here really is that I think diversity is going to be what we get in the future as people try to get more and more computing out of a limited power budget and a limited silicon budget. Okay, so that's the background really. Where does the HEP Software Foundation come in? Well, I think about 5 years ago we realised that the LHC experiments, Bell 2, June, and of course our colleagues in nuclear physics as well, face very similar challenges, and that we were going to have to greatly evolve our software in order to meet those challenges. And that this was a hard problem, and we would need to exploit all of the expertise which was available to get the parallelization and algorithmic improvements that we needed, and to adopt new approaches to overcome the limitations of, well, I say today's code, yesterday's code, because the code that's in production was not written today. We wanted to reduce duplicated efforts and share knowledge, and make sure that when people were starting anything from a new experiment to a new project, you wouldn't start from scratch, but you would build on the best of breed. So the goal of the HSF is to facilitate coordination and common efforts across HEP in general, and our philosophy is to try and do things from the bottom up. I think Tori coined the phrase a do-ocracy, and it's one that we still like to use the HSF. So although we were doing things from the bottom up, we did want to gather the community together and describe a kind of global vision of where we wanted to go with software and computing. So about 4 years ago now, our first sort of big challenge was to write what was called the Community White Paper, which was a large survey of all software and computing activities inside of high energy physics, which is available on arXiv and in CSBS. And this got a very high level of engagement from the community, as you'll see from the number of people that we had signing the paper, the institutes, and indeed the scope of the paper as well. Now, last year we updated some of the CWP chapters, specifically focused on the challenges for high luminosity LHC, so the ones which really consume the vast majority of the cycles. So that's analysis, reconstruction, simulation, and event generation. And that paper was published last year, and it was part of the submission to the LHCC, which is the committee that actually reviews preparations for the LHC, and in particular there's one committee that looks at software and computing. And the HSF has also taken on a role in advocating for software, and we did that a couple of years ago, engaging strongly with the European strategy update process, and now with the SNOMAS process in the US as well. And I think in the interest of time, I won't spend any more time on this slide, except to say that message about the importance of software and computing did seem to get through to the European particle physics community, and our august leadership made mention of software and computing as being essential in the development of our strategy for the future. So, okay, what does the HSF do in a more practical sense, as well as writing things down? Well, one thing that we've traditionally done is workshops, which bring the community together to discuss areas of significant interest. and to encourage crosstalk between people in different experiments or different regions. Often we organise these things in conjunction with the WLCG, which is the organisation that runs the computing for the LHC, recognising that there's synergy between the two areas. I have to say that 2020 was not the year that any of us expected, and so we had to postpone our intended face-to-face workshop in Lund, and instead we replaced that with two virtual events. One which we had in May that focused particularly on new computing architectures and the portability and sustainability questions that come up there. And then towards the end of the year, we had a more focused software workshop that looked at a whole number of different areas, training, event generators, simulation, and even a nice general R&D session as well, and that included a very nice presentation from Markus and a discussion about what was going on inside the nuclear physics community. In 2021, we probably won't do exactly the same thing, and I think we might switch to a focus on smaller, more one-shot events. I think there was a sense towards the end of last year that people were starting to suffer a bit from Zoom fatigue. But of course, we're always very happy to get people's input on what the best way to organise the community is without exhausting everybody with too many meetings. So the more day-to-day work of the HSF is not focused around workshops, but we have a number of working groups. That's kind of our main engine of activity. We have 8 of these, and in fact 2 of them we'll hear about later on in this meeting, so I won't mention anything to do with them. Instead, I'll just give a lightning tour of some of the activities which are being done inside the HSF in the different working groups. That will give some people an idea of where they could get involved. So we are good at giving people advice on how they should deal with some of the boring, but it turns out to be practically quite important lessons about software in terms of making sure that you have the right copyright and license on your software, and also giving people advice as to how their software can build as part of the larger ecosystem, so what the best practices are both to develop software and to make sure that it gets packaged properly. And here we have quite a lot of convergence in the community on the SPAC tool, and that's being actively investigated by a whole number of people inside of the HSF and the wider community. And I think the group is planning to have more activity around packaging in the coming year. Just flipping quickly to event generators. Of course, these are the base of all of our simulation. And in the LHC, what I should say is that in run 1, using only leading order generators, they were not very large contributors to the CPU budgets. But they become increasingly important for precision measurements, especially at high luminosity LHC, because you use higher order generators and you also have to tackle technical and physics challenges arising from negative weights. So the HSF actually started an activity here which is quite unique in terms of bringing the generator community together to look at computing aspects of generators which haven't really been done before. And that working group has been active in fostering collaboration between the experiment experts, software engineering teams, and the generator authors themselves. So there was a dedicated session actually in the November workshop that I think highlights progress in many of the areas there. So once you have your generated event, of course, you want to simulate it, and that is a major consumer of LHC grid resources today. In fact, I think it is dominant for at least 2 of the 4 LHC experiments. And with higher data rates in the future, we're actually going to need more simulation. So our simulation has to get faster, but without losing, of course, the physics accuracy that we need. So active areas of investigation are things like machine learning, where people are usually targeting the calorimeters, which are very expensive to do full simulation for, and a number of different machine learning techniques are being used. And one point that the working group has been addressing is, when is it good enough for physics? Because that's the key point, is when is it good enough that you can actually use it? At the same time, GPUs are being seen as a real target. Some architecture convergence there in terms of the what's happening in the new supercomputers. And here there are two particularly interesting R&D projects, the Celeritas project inside of the US and the ADEPT project, which is based at CERN, but also with some UK involvement, who are targeting doing electromagnetic calorimeter simulations on GPUs. And this is a very good way of factorizing a computationally expensive part of the simulation, but then combining it with using Geont4 for the rest of the simulation. Again, there was a very nice summary at the simulation session of the last workshop. Turning then to reconstruction and software triggers. People will be well aware that hardware triggers increasingly don't do the job that we need. And so more and more initial reconstruction happens in software, and LHCb and Alice, I think, are really leading the way in terms of developing this kind of triggering technique. Here you have to deal with tremendous rates when you're close to the machine, and a lot of effort has gone into rewriting code for GPUs, which actually, when you look at the physics again, the physics can even get better when you do these kind of rewrites. There are a number of lessons which are learned, and people are also using these sort of high rate reconstructions combined with very fast calibrations to give you real-time analysis where you can produce analysis data products very close to the trigger itself. And that's a really great way to squeeze more physics out of the limited budget. And in fact, I would say that was the work that drove a lot of the interests in GPUs inside of high energy physics. Then moving to the analysis side of things, scaling up our analysis for LHC experiments is a very big deal. There are a few techniques which are being used. One which has actually been borrowed from nuclear physics, I think it was pioneered by Phoenix, is the idea of an analysis train, where you take something like an AOD object and you run many analyses on that inside of one computing job. That goes very well also with techniques like tape carousels, which are being developed by Atlas. And I would say that the other facility aspect of analysis, which is very interesting, are analysis clusters, where you might build a machine that is very specialist for analysis operations and has sort of very good I/O operations compared to generic grid facilities. Of course, just reducing the data volume makes a big difference. So CMS's amazing 1 kilobyte nano AOD here is a cornerstone of their high luminosity strategy, and improving the way in which we write analyses, so declarative models, things like our data frame, and also many Pythonic ways of doing that are very good for helping our analysts actually write their analysis in a more efficient and sustainable way. And there's more, of course. I mean, there's been a bit of a sort of whistle-stop tour of the working groups. But one thing the HSF is also doing, because of this convergence around GPUs, is we've started to organise the Compute Accelerator Forum in common with our colleagues in CERN Open Lab and the Software Institute for Data Intensive Science, which organises a number of European computing and software engineering places as well. In fact, we have the next meeting tomorrow, which I see I forgot to put the link in for, but I can send it around for people who are interested. And one of the other things that the HSF does is organise the Google Summer of Code and Season of Docs activities for the community, and that's very helpful for the community because it allows smaller projects much easier access to programs like GSOC. And we have a number of other activity areas that can provide a meeting point for other things which are going on. One very interesting one is, for instance, the Phoenix event display, a web-based event display, which is a really nice development and getting a lot of interest from different experiments. So to sort of try and round up, so we don't blow all of our time, the outlook for the HSF, well, it sort of relies on the fact that in particle physics we're inherently international, and we do have a very good tradition of cooperating in many different domains. And in the HSF, we're trying to foster this kind of vision of diverse R&D, and sharing ideas and sharing projects where it makes sense as well. And one of the other things that we do is we help attract funding into this area. So we have recognised links to many of the main players, and we help people to make funding applications as well. I think nuclear physics, being a very close cousin of ours in terms of software and computing, we're actually extremely excited about the prospect of working more closely with you in the coming years. And we're very happy to be a new partner in the Roundtable series as well. So I think that that's probably a good place for me to stop. And then maybe we can move on to the discussion. But I'll just flash up that there's a few links there if you want to get more involved with the HSF. And that gives you some of the links to be able to do that. And here I'll stop. Thanks.
Thank you very much, Graeme, for this great overview. Are there any questions on his talk? So we are perfect on time. So we have time for a couple of questions. As I don't see immediate a question, let me ask one. What about work you do regarding outreach or maybe promoting the role of software and computing in HEP? I mean, it was very nice to see in this screenshot which you had from the European strategy update that they realized the role of software and computing and also the role of collaboration, common projects. But has there been any outreach work you did in this regard?
Yes, so this is one of the areas that we've been trying to be active in. So the HSF actually gave a presentation on software R&D at the European Strategy meeting in Granada almost 2 years ago. And a couple of us who were involved in the HSF were also authors of the strategy document, which came out of that process as well. And we're lucky enough that we sort of clearly attracted some interest from CERN management. So we've also given talks, for instance, at the Scientific Policy Committee here at CERN. So I think the way in which one does this is you engage with these processes where you're able to, and then I think that gets the management to pay attention to the fact that you exist. And if you seem to be doing a good job, then they will invite you to become more involved in those processes. So in terms of snowmass, I've not been quite as much involved in this one, but I know that people who are active in the HSF working groups and the HSF have put in quite a few of the snowmass LOIs. And we did in fact submit also the high luminosity LHC computing document that we wrote for the LHCC. That was also submitted as part of the snowmass process. So yeah, I think rolling up one's sleeves and getting involved in those policy discussions is a very good way of raising the profile of software.
Thank you. Are there other questions to Graeme? I don't see any, but let me ask. Oh, please go ahead.
This is about careers. What activities do you have in encouraging development of diverse careers that prepare young researchers for a career inside or outside of academia?
I think I won't say much in terms of answering this because I think that Sudhir will cover a lot of this in what he says about training. But let me go a little bit beyond the training aspect, which is to try and give people good core skills which we need in our community and of course is needed by society outside of HEP as well. We don't employ anyone, so we can't give anybody a job, unfortunately. But I think one of the important aspects of agitating for software and raising the profile of software is so that the hiring committees in universities and at labs recognise that they need people who have good software engineering skills also in their physics departments as well. So we are trying to, through bodies like ECFA, make sure that people know that this is a key skill which actually has to be retained inside the community. So we hope that we get the message through to the leaders of the faculties that actually they do need people with software skills, and that would form part of a balanced department, as well as, you know, building the detectors and doing the analysis and everything else.
Thank you.
Graeme, if I can, Markus.
Please go ahead.
Yeah, I have a question a bit more about philosophy. It seems to me that recent developments of the software chain at CERN are aiming and founding rare events. So you go up with the luminosity and you are study rare processes, and that's how the full chain almost is designed. Why at the Electron Ion Collider we will be interested to almost each event that is in the detector. How you think that we can merge this kind of two philosophy together in order to benefit for all the work which is being done?
Right. I think that what you say is very true for Atlas and CMS in particular. And one of the reasons that they will actually stay with a trigger, even at high luminosity, is because the physics program has a large component, let's say, it's not that is based on rare events, high PT events. But I think if you look at certain aspects of the what's done inside of Atlas and CMS, for instance, low mass dijet resonance searches, and then you look at the physics program of LHCb and ALICE, you actually start to see that that's not the whole picture. So I think there's many things which are going on at the LHC which are actually quite, I mean, ALICE of course is an ion experiment and be quite a high energy one. And the way in which LHCb does its B physics, I think it's been characterized by some of my colleagues as, you know, you're searching inside haystacks that are composed of needles. There's signal inside of almost every event. So I think there are avenues to explore there that have a different a different goal, a different physics goal that's closer.
I was thinking that even ALICE, which is already running at reduced intensity, at high luminosity will concentrate on trying to catch more central events with the charm productions and so on, and not on the overall counting of the number of produced hadrons per event.
I think to comment more on that, I think I would have to involve some of our ALICE colleagues that are, you know, perhaps a bit closer to the physics program. But I think that the trying to exploit the power of the luminosity that we get at the LHC in certain physics channels is always going to be part of what we do. So there's always opportunity, I think, there to foresee physics programs which are a bit closer to what would be happening at the EIC.
Okay, there's also an interesting comment about LHCb by Eduardo, which is going in your direction and which is good. Thanks.
Yeah, thanks for the question.
So maybe that was a good transition to the next talk, mentioning Eduardo's comment. Thank you, Graeme, for the great overview. Graeme presented the various working groups, and we will have an in-depth look in two of them. Next, Eduardo Rodrigues from University of Liverpool will tell us more about the activities in Python for HEP. Excellent.
Hi everyone. So indeed, I'll focus now on the PyHEP, which stands for Python HEP Working Group within the HSF specifically. So first of all, PyHEP actually means Python in High Physics. Don't get no, don't think that this was just a focus on HEP, but it really is particle physics. But of course, Python PP would not be so easy to say and so recognizable. So that's right. But it really was from the beginning particle physics, and you will see from the communities involved in the discussions and workshops and so on that this is embracing the largest possible community. Everybody is really welcome. So first of all, of course, this was Python. We say that, so this is an obvious slide just to show that in some way 2019 was already the year of Python, where you can see from the popularity of programming languages in terms of searches for language tutorials are concerned from this PyPL website. You can see that Python took over from pretty much everybody already in 2019, and things are going up still quite a bit, whereas, for example, C and C++ are more or less flattish and so on. So it's certainly, and this is a log scale, by the way, so it really is a big difference. You can see here that Python grew up the most in the last few years. This is understandable given that the software ecosystem there is absolutely huge and used by a very big data science community, where things are very well documented. You also have great community support, so typically it takes you probably minutes or hours the maximum to find or get the answer to your problem online. So that's really a huge benefit. So if we step back a few years, and just as Graeme, I'll come back to the community white paper. I took here 2 snapshots where Python is mentioned. So Python was already identified at the time of the community white paper, the preparation of that paper, as a first-class language for particle physics. So this is written here, and it emerges a language of choice for the data science community, etc. For HEP analysis, increasing sustainability, blah, 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 etc. And we needed an investment if we wanted to have Python really as a first-class supported language. So thinking longer term. And this is yet another one mentioning also root and the need to have Python bindings for this big analysis software package that is root. It's central to us. So a lot has happened in the meantime, as you can imagine, not only in the evolution of PyRoot, but also community-wise. And given that this is an HSF presentation, I will focus on the community activities, but I will also have one spare slide on root to be a bit more comprehensive. So particle physics in Python. So this is taken from the workshop that we had last year. So you see that we had 400 respondents roughly, so quite a bit. And clearly shows that the interest in Python, most of the people attendees, was the availability of general purpose data analysis or machine learning toolkits. Also the interest of having root via Python, so PyRoot was very on top of the list, as well as the development speed and efficiency. So this is something we typically say that Python is really nice and efficient when you want to iterate very quickly and do something, some quick design, some quick checks and so on. I'm not saying this is a solution for everything, but in many cases, certainly in the very iterative process of doing analysis, this can be very helpful. Just for the sake of exemplify the interest that we're having in the community, this is a nice study from a colleague of mine from CMS, where he profited from the fact that on GitHub you can have since a few years now the software framework, so CMS software, CMSW. So he looked at non-forked repositories from users. You see from the statistics, this is quite a large number of people and repositories, non-forked repositories. And if you look then at the plot on the bottom right, you can see that there's clear evolution of Python taking over and taking up quite dramatically since 2015 or so, compared to C and C++ again. By the way, the Jupyter component there, it's pretty much all Python as well. So it just shows yet again the takeover of Python, the popularity of Python in the field. I could also show you, this is more, there's a few slides probably I can give you for information. This is a similar study that myself and a colleague did in LHEB, also in this case looking at the usage of root itself. You can also have for machine learning, and this was, of course, I'm not presenting everything here, but you can see that already 2.5 years ago, Python, root from Python or in macros, standard C++ macros, was used 50-50, kind of sharing the cake already. And things have only been going up for Python in the last 2 years, as you can probably imagine, just from these tendencies as well here in the CMS study. Okay, so one slide on the root, because it has evolved indeed enormously over the last few years, and this was, I think it's fair to say, one at least partially a consequence of this community white paper and the fact that the community identified the need for this. So I'll give you a couple of links, recent links from an ICHAP talk on the root and tuples, so the modern tree for the 2020s, I would like to say, and friends coming from root. So you see there's many improvements on the design, interoperability, the Pythonizations, also the way you build it and so on. And another talk more here specifically on PyRoot, where I would like to emphasize the fact that for me at least a game changer has been the development of making root available in Conda, so just as you would do in a standard environment for data science, just as an alternative to a pip install, you can just go ahead and install root. And this is also not to emphasize, I think, the fact that it was largely done from the community, not the root team itself. So we really see it as a community engagement that has been increasing over years, and this is very positive. Also to mention here that all of these things have had an impact. So this is actually on the right, this is an article from the CERN Courier on the first publication of a full analysis likelihood from Atlas in this instance. What is important, I wanted to emphasize here, is the fact that in this publication, a very nice one, not only it was done with the standard tool C++, but also with an alternative tool that is a pure Python package. PyHEP in this case. So you see that really things are we're now getting even publications where Python tools that have been developed in the last 2-3 years are making it all the way to the as something really used for producing the final results. Okay, so coming then to the HSF and the PyHEP working group itself, I'll talk about the working group, the workshops and the activities and some community projects, because this is all about community in the end. By the way, there's a lot of information on the backlab slides if you want, and also very often the pictures are linked, so you can follow directly there. So Graeme already mentioned these working groups in HSF and some activities groups. I want to focus on PyHEP and some of the workshops and events that we have done. Just mentioning that this activity in fact started more or less 2.5 years ago in early 2018 and became recently last year formally a working group. We have several communication channels. The main one, GitHub channel, now has a fair amount of people registered. You see 160 and growing all the time, so it's very nice. And you also have specific ones for, well, topical channels if you want, or if you want to discuss more. Sorry, indeed this link. So if you want to specifically discuss fitting or histogramming or some other things, visualization, you can go directly on that topical channel, but otherwise you're more than welcome to register to this channel. And we really embrace everybody. So broad is good, as we mentioned here in our reason better, but the broader is even better. In terms of community projects, I mentioned, so root is an obvious one, but what is nice to see is that in the last few years, indeed, several software projects, more or less with a certain number of packages providing for data analysis has seen the light. You see Coffee, FastRep, SciKitRep, which is something I work on, and ZFit. They work on different purposes, so altogether they actually build an ecosystem, and that's a nice thing, profiting from each other, not to be reinventing the wheel. And this is a little nice page here to show that some of these problems, issues that Graeme talked about recently, a good way really that we think is the way forward is to tackle them as a community. And so there's no surprise that should be no surprise that we have these all of these series of projects that have seen the light. Also talking about working group activities, there's a strong link with training, and you will see that in some of the contents of the workshops in particular. So these are the workshops. So we have been doing them since 2018. So we had three by now, and so this clearly is the way for the community to engage with each other and have an opportunity to discuss in the old times face to face. So in smallish committees. So around 50-70 people attended these two workshops face to face. What I also wanted to mention here is, aside the fact that yes, there's a fair amount of a fair percentage of participants coming from the huge collaborations LHC, you do see a lot of other communities and experiments coming along and contributing, either with presentation or just as a quote unquote as a participant. And likewise, you see also a fair amount of participation from IT groups, research software engineers, and lab staff. So this is by all means not at all just analysis physicists, and this is very important for us. Okay, talking about I'll have a few slides to finish off almost on the last workshop, so the one from last year, so which was a special one in many aspects. Of course, first of all, it was special because, well, at the very beginning we were engaging. We did engage with the big, huge SciPy community, and that's the reason why we had co-located in time and also in place originally with the SciPy in Austin, Texas. But in the end, of course, everything went virtual, and we had to organize things accordingly. This was not negative in the sense that all of a sudden we could go for a truly global event with participants from all over the world. And that you can see that in the backup slides, there's quite a lot of information on that. And you can also see from the level of interest, now being a virtual event, we jumped from 70 people to 1,000, where we had to limit 1,000 registrations to be sure that we could provide the Zoom conferencing system. This is again, this is plenty of active links for the workshop. I want to emphasize, this is nice to see that we have a reasonable amount of sponsorship, even from the Python Software Foundation, which to me proves that there is a clear interest in these activities. That's great to see. Okay, so in terms of diversity inclusion, if you compare this plot with the previous one here, I see this is the LHC experiments. Now the LHC experiments is just that, not even half of it. There's many small experiments being represented as well by one or two participants or a few. But what has changed going virtual is that we have a huge amount, almost 40% of participation coming from undergrads, postgrads, and also other communities such as theory, instrumentation, and simulation. This was not negligible at all overall. We saw that from the surveys. So that's really reassuring that we are embracing, and there is an interest going beyond what we had started in a small circle at the very beginning. You also have here a logo kind of picture with all kinds of logos that we could collect. You see quite a few collaborations, and some of them are absolutely not LHC or high energy physics. So we have neutrino physics, astroparticle physics, and so on. On organizational aspects, this is a big slide that I like to give an overview, to say that we had tried some nice things, I think, for this virtual event, starting with the fact that we actually had two sessions, one that was Atlantic friendly and one Pacific friendly. So this was to try and be more global, and we encouraged really strongly, in fact, notebook presentations. So people would put their Jupyter notebooks on a GitHub public repository with the button to launch it in binary, and then every participant could launch the thing and run it interactively live at the same time as the speaker was presenting. This was particularly useful for tutorials, as you can imagine. We also put everything on including the recordings that were captioned, by the way, on this was all on the node, also on the workshop agenda, and on the HSF YouTube channel that we have a dedicated list there. So in terms of conferencing system, I already mentioned that the thing maybe more interesting, less known, is that we try to use Slido. So this is a kind of an online platform that allows you to crowdsource questions. So any participant can put up a question that you'd like to give to the speaker, and this is upvoted by everybody, which means that you end up at the start of your Q&A session with a list of most popular questions. So the most popular questions are answered during the live, which was for us typically 10 minutes, and then everything else is put on the Slack topical channels, and everybody can continue the discussion, particularly for all the questions that could not be answered within those 10 minutes. And I have to say that the participants had really played the game, and this was very nice to see. For completeness, I give you here a list. What I wanted to mention more is, aside the fact that we had two keynotes on theory, and astronomy, we had roughly a ratio of 1 tutorial to 2 nominal presentations. You see 20-minute presentations where we had 45-minute tutorials. So this was really to give a bit of a training here, not just a standard workshop. But of course, this would have worked even better maybe face-to-face, but that's reality. So finalizing here on the plans for this year. First of all, it's clear that we will organize again a PyHEP workshop. We're likely to tag along again with SciPy, and this means roughly mid of July, given that the SciPy is now scheduled for the 5th to the 11th of July, and it's still not decided whether they will go virtual or they will try to go face-to-face, so we'll follow that up. We plan again a good mix of talks and tutorials, and really your engagement and participation is welcome. I hope I have mentioned to you probably far too many times that we have a broad community. Everybody is more than welcome, either as a participant or either also submitting tutorials, talks, and so on. We also going to start this year a series of topical meetings, because this is something that came out of the workshop as particular interest, and we will follow a bit what you may know, this Python 3 module of the week. So we will kind of do a meeting a month with the name Python module of the month, where we will try to focus on a library that is particularly relevant, say for data analysis and particle physics. Why not nuclear physics specifically if you have something different? And we try to do that hopefully regularly every month, not to have too much of a Zoom fatigue, as Graeme was saying. And I should mention that the first one will be early next month on number, and you have a link again to the indicators there. So just to finish off, let's collaborate, and I think really your perspective will be enriching, because it's bound to be slightly different from ours in various aspects. And I give again a few links if you want to follow things up immediately. So for the discussion, thank you.
Thank you very much for this very interesting overview about your activities in the Python and particle physics working group. And in particular, congratulations on this workshop where you had to limit at 1,000 participants. This really shows the interest in Python for our type of science. Are there any questions? Yeah, David Lawrence has already raised his hand. David.
Yeah, hi, Eduardo. That was a very nice talk. I enjoyed it very much. I'm David Lawrence at Jefferson Lab. I just wanted to ask, you kind of pointed out how the outside community, or the non-particle physics community, is very big into Python, or has been growing very big into Python for quite a while. And we also have seen Root really grow to support it more and more. I'm kind of wondering if there's been any indication that outside or other disciplines of science besides particle physics have moved towards adopting Root in some way, or do you see a point where people in the particle physics community might start moving away from Root towards other tools that are being used by some of these other disciplines of science?
Yeah. I can't speak totally for Root, although I do know that Root is used by other communities. I think there's actually even a recent article from CERN where they were using for some medical applications, I think. So Root is established, and it is used by several communities. For Python, I would say it's more in a way these are two different communities. But for example, I use both, right? For coming out of these projects, and there's a few projects I could mention here. Oh, sorry, these projects here. So particularly, I use things from both. So from both Root and these projects. What happens is that Root now is also connecting better with the data science. So it has a bit of more bridges. This is something that follows from the feedback from the community, obviously. And then you have tools that are already built into the community, so they start immediately building on top of NumPy, SciPy, and so on. But it's difficult to say more without going into I don't know, politics. I don't know exactly what you wanted to know about that. For me, at least, I see the positive thing. and there's various ones. First of all, competition has never been bad, and in the end, the user will gain because they have better products and they also have more choices. Right?
Yep,
That
yep,
answer
yep.
this question?
Yes and no. sometimes that works against you a bit, but no, that answers the question. Thank you very much.
Are there other questions for Eduardo? I really like this idea of the Python 3 module of the week, given all these very useful data science modules which are available.
Just to say, by the way, we have always been engaging and being in touch with Root. So it's not that you should see this all of a sudden these things as two separate communities. I would not, as far as I'm, as you can always gather, I'm quite interested in all of this big data science ecosystem. I think we should work together, and that's what has happened. Root has always been a participant of the workshops, for example, and it should remain like that. We all have to gain.
And they also, of course, folded in new data science standards, like the popularity of these notebooks. Nowadays, you then also have had root books. Would you like to make? You highlighted that you had this very nice notebooks GitHub binder combination for your tutorials. Do you see that this is something which could be also used beyond tutorials, but really become also really active part of analysis workflows at experiments?
Yeah, sure. Honestly, it is already been the case. So speaking, I know a bit better, of course, LHCb, just because I talk more directly with many colleagues, but things have dramatically changed there in the last couple of years. It is true that maybe 2 years ago people were looking a little bit at Jupyter notebooks. It sounds good. Maybe I will check it, and then they started writing indeed tutorials or hands-on with that. But things have evolved now, and what you see is that notebooks are not just being used for tutorials, but also for presentations, and also as kind of a script, or even as a means to share the analysis work that is being done with their supervisors. So that I work with a student, for example, and he typically sends me notebooks, because then I can immediately see or just even the link, right? But the idea is that in the notebook you can then see, immediately see more information. You can have access to the code and also some of the plots all together. That's a bit easier. Whereas in the old times you might send some code or some links to a directory on your Linux cluster, and then at the same time you would have some PDF with some plots, right? And now it's much easier to put everything together. So I think things are evolving quite a lot, and we're profiting largely from the experience in the data science world there.
Great. Is there any last chance for questions to Eduardo? Otherwise, we move to the next presentation. Thank you so much. We already spoke about tutorials. So the next part will be about training, and we have Sudhir Malik from University of Puerto Rico, who will give us an update on the training activities of the HTTP Software Foundation.
Well, good morning, everybody. Thank you for giving this opportunity to connect with the nuclear physics community. It's not the first attempt. The thing is, I have strong initial connection with Jefferson Lab. I started my career at Hall C with GE and Experiment back in '97. So, and it's good to see all Henson also here, who participated in one of our training sessions at JLab workshop in 2019. All right, so anyway, I will talk about the training working group of HSF, which I co-convene with 2 other people. Since this is the sort of first time connecting with this at this level, I would like to give some overview and motivation as I come from HEP community. The thing is that this is just to build up the foundation of why training is important, which I think we all know by now, but just in case to compare where we are. So as you all know, the scientific collaboration these days are pretty big. We have thousands of collaborators from many institutes involving many countries. Here is a list of different big HEP experiments, and also LIGO, and also some past HEP experiments, DESER and CDF. As you can see, the collaborations have grown bigger and bigger, and also multinational, and they are like big enterprises. The map here shows that this CMS collaboration, and basically the sun actually never sets. So some of your collaborators always working or needs help, at any time of the given day. So collaborations have mushroomed. So the new paradigm that the users find themselves in is that there are several experiment challenges to be met, that may require know-how. There are several computing tools and physics analysis that we aim to do, and they're all intertwined. By that I mean, if you're good in computing tools, you can be ahead in physics analysis also. So also the experiments have a very long lifespan, typically 20, 30 years, and there's enormous data. And then also, since collaborations are big, not everybody can be based at the host lab, for example, CERN, and also the computing environment is highly distributed. So the point in saying this is that given the complexity, it's very important that there is a need for an organized training if we want to achieve big discoveries from the big science that we do. So this is the scenario where we are in for the last few years. The HEP software ecosystem is very complex. We need software at every single stage, be it physics generators, detector simulation, or even reconstruction. And then there are other new tools that have crept in that makes our physics easier, in the sense that we have enormous data, and the physics we are trying to find is just few events. So we not only need tools like machine learning and artificial intelligence to reduce our backgrounds or improve our trigger or whatnot. So there is so many things that any newcomer is overwhelmed by, and there is a need to have some sort of training in place where they can jumpstart to make their contributions. I cannot emphasize more. The training has lots of benefits because computation is central element of all that we do in this era, and also this will the new tools and workforce HEP domain knowledge is needed to propagate the work that we do. We also feel that investing in this kind of training, and software training especially, is critical to match HL-LHC requirements. I'm specifically talking for LHC, but I guess the same thing is applicable to any basic science because we always struggle with flat budget. Also, investing in training leads to preservation and propagation of knowledge, which is very important. We need to pass on the skills of our trade to the younger generation. And also investing in software skills is not only important to actually build requisite software infrastructure that we need, but also change the norms of our community, create role models, and promote career paths, as was one of the questions that was asked during Graeme's talk. Also, we need to transfer skills to our next generation of postdocs and students, and training leads to sustainability. So investing in training is sort of key to the big science that we do. Now, there are many flavors of training that exist, software training that exists in different experiments. Remember that goal of every experiment is not the software, but to do the physics. But being expert in software is what it takes to do physics, given the challenges. So here I've enlisted on this slide different trainings that are happening in different experiments. As you can see, they all have some sort of training. Some experiments are far ahead, or they're more established. Some are new, and some are still projects and building stage like Dune and so on and so forth. And there are also some trainings that exist in general, besides experiment specific, like CERN School of Computing, Gridka School, and recently CODA-CEP School that has been happening at Princeton for the past 2 years. So there are things that exist, and it's not that we are starting from scratch. So that's very important. But some of these trainings are very experiment specific, which is very natural. However, since we may have a lot of things common, it's important that we look at the need for common software training, which I mentioned here. As you can see, the limitation which I just mentioned, that trainings, they are fragmented and some of them may be redundant, is experiment-specific flavor, and sometimes training are difficult to support over time because people, sometimes leave, sometimes the people in authority in experiment fail to understand the importance of training. This has been my experience. People say one thing, they do another thing, but somehow I think the push for training has made the sense go across to higher ups that this is very important for everybody says it's important, but when it comes to doing things, it needs money, people, and time. So that's where the challenges basically come in. And also, no single entity has a mandate to organize these different efforts into a common effort whose impact would be much more greater than some of its parts. And that's where HSF basically has an important role to play. So some of the training challenges, besides what I mentioned, are that not all funding agencies have the same priority for training and education. So for example, in US, DOE cares more for big things, and NSF cares more for education. So they have different priorities. Though I think DOE is also bending its mind towards some of that, because it's important to succeed if you don't have enough manpower to do things, and that's very well trained. Also, training activities are not always valued, as I hinted before. The thing is that will the efforts in this area lead to improvements in software efficiency and scalability? So this is an important thing to realize, that this is the way to go. Also, new tools that keep coming up, they require investing in training, because if you don't train people, the new tools, you won't even know how useful they are or how useless some of them could be. So it's important to train people to iron out what is best in software. Also, training needs to evolve, and that means there has to be continuous support for training within the experiments within our community. Okay, so this is where, as I mentioned, the HSF has taken a good role with the help of it's some of the US partners. So the mission philosophy of HSF training is that people are key to the successful software. They are the real cyber infrastructure that underlie a sustainable software. Our mission is to help the research community to provide training in the computing skills that we all need to deliver high quality physics results, and also the software that is sustainable. And the philosophy is that we build training activities and materials for a common good. And so that we have a strong community of instructors and participants, and where we have a feeling of community ownership, because we are all humans, so we want to feel connected for something common. So the training style that we have is mostly hands-on and student-centric. It's experiment agnostic. It better be, because we are looking for the common grounds, and it's reusable and open and accessible. So that's very, very important. And of course, the goal is to sustain and also scale up our activities. So since our inception, we have trained about 700 participants. I would like to mention here that our training motivation, the idea that we picked up was from Carpentries, which has been very successful in giving software training to almost everybody that needs it. But we have their motivation, which we picked up for our field of particle physics. Some of the training partners of HSF are IRS-HEP and FIRST-HEP. They are the NSF-funded projects. FIRST-HEP is dedicated mostly to training, whereas IRS-HEP is a bigger body with a component that focuses on training. So it has basically aligned very well that we have HSF that has come up, which is an umbrella organization, and then we have funding that is provided by, for training purpose at least, from these two organizations. And I hope with these things we can climb up the pyramid that I show on the right side, where at the bottom we have the basic courses that we do for every, which are of common sort, and then at the top are the mentors who actually come from the bottom of the pyramid. So this cycle is something that is important to propagate. So here on this slide, I've put some links which point to the training material that we have. One thing I want to emphasize is that besides the material itself, we have a growing community, and it is sort of, we put pictures of people there so that, you know, it's a way to sort of, you know, recognize them, what they have done, how many times they have trained. So in case they apply for jobs or something, you know, there is a proof of that work besides some letter of recommendation, which I think the industry doesn't care. It's word of mouth mostly, unlike when you apply for a faculty position. So the other thing was that we time to time have a blueprint workshop where we evaluate what we are doing. We try to plan our events and sort of hackathon. So we are pretty active, and I would encourage you to look at these links. And our goal here is about openness. So here I enlist the training lessons wish list that we have. The different color coding is telling you about which are ready, which are in development, and so on and so forth. So if nuclear physics community has its own ideas or wants to benefit from what is already there, you're absolutely welcome to become a part and contribute and grow together with us. This slide is showing the trainings we have done up to the date. The big red mark is specially put to show that how the inception of a COVID pandemic interrupted our flow of thought, like what we are supposed to do. So eventually we moved to virtual world and adapted very well and very effectively to that. So we have been pretty active despite the COVID thing happening, but it took some time to rebalance ourselves. So here is an example of the training. So before that, we had in-person training, and I'm sure when the pandemic is over, we will have more of in-person training. So there is some advantage of in-person versus virtual training. Of course, I'm not going to go through this list, but you are welcome to look at it. But most important is that the positive thing is that we are all human, so we need a human, you know, environment to work. So that's you can have a professional touch, a personal touch when you have an in-person training. However, I wouldn't say negative side, but it is still negative means that there are cost travel involved and then there are funding restrictions and so on and so forth. So there's plus and minus to in-person training, and then you need you know, an infrastructure. However, when you do a virtual training, which I mentioned was COVID enforced, we can actually scale up the attendance to a few hundred because all you need is a good computer connection as an infrastructure. The positives are many. You can have wider audience. You can have people who are more likely to participate. So we remove the funding, travel funding restriction, and so on and so forth. So the material that is given is also preserved. It is preserved in both cases, but since this is virtual, we make sure that we have videos and different platforms to communicate while the training is happening and after the training is done. So here is a snapshot of the C++ training, which was very popular, and the second iteration of this happening this month. The spots got filled up within 2 minutes. So these trainings are becoming very popular and shows the hunger that's out there. Here is just a bit of proof that the training actually works. So if you look at the histogram on the right side, the top part is showing that before the training begins, the beginners are many and experts are none. And after the training has happened, of course, you still don't have experts, but you have the histogram bar shifting to the right. So people are learning, and eventually after a couple of iterations, they will perhaps become expert. Here is a great example of a journey that Meron Evans took in HSF. He was a student. He participated in workshops to learn. Then he mentored several things, and now he is my co-convener within 1.5 years. So this is also showing that that people can also have a good visibility and career path, and depending on how much they participate. So I wanted this as a special mention. And also here is a slide that shows our future plans. This is heavily worded, but I have put in bold what I want to emphasize. So in future, we want to focus on community of individuals, which is very important. And as somebody asked the question about diversity, that is our focus. That is something that's at the back of our mind, and also some sort of requirement from U.S. funding agencies at least, and of course at CERN also. There's a lot of emphasis on having a wider community. We also want to emphasize on core team that can support our mission over a long period of time. We also want to build regional and local capacity because we think that's where the strength lies. The more you propagate, the more you have chances of surviving and doing well. And also equity, diversity, inclusion, I mentioned before. And we also would like to have a mechanism of feedback from different communities. We do have surveys, but I think eventually we want to have this on a bigger scale so that we can be under check that what we are doing is actually beneficial. We also have, and we also continue to plan to have brainstorm session for experts so that they can improve the material and also, of course, improve documentation, which is always a continuous process. The last but not the least, and actually this very important thing is to have a long-term financial support model because we need some minimal funding for virtual training also. And of course, in-person training requires more funding. So some sort of that model of financial support is needed, which has been so far supported by RSHEP and FirstHEP NSF grants. And of course, with some support from CERN also. So we also want to expand this collaboration of our work to nuclear physics, neutrino community, and other related communities like LIGO. Neutrino, we have had some parleys and going on, and with nuclear physics also. So I think I really look forward to this participation because there are so many ideas and so much talent out there that we need to tap. As a backup, I just wanted, if you are interested more in what HSF has been doing, I would refer you to the talks of my past co-conveners Samuel Meehan and Killian in your spare time. And I'm ready for any questions that you may have.
Thank you so much for presenting all this dedicated work you do for training. I'm quite impressed by the successes you shared. So both the histogram and also the journey of your co-convener. Are there any questions? David.
Yeah, it's a very nice talk. I just had kind of a question just to get an idea of the scope on this, because sometimes in nuclear physics we're at a little bit different scale than what is done in high energy physics. And the people who are involved in this effort, how much of their research time would you say is spent on the training aspect of this? Is this the primary contribution that they're having to the scientific effort?
So I'm glad you asked that question because that is the big challenge we face. So for example, a student may want to contribute, but their supervisor may say, that you shouldn't waste your time. So these are the kind of mindset that we have been fighting, making supervisors aware that it's not that the supervisor's funded project has to succeed, but our field itself need to succeed. So I think many students have been willing to contribute, and I would not say that's not a challenge. However, I think the thing is that since learning is aligned with also what they do, and since most of them will land up doing jobs outside academia, this is a sort of thing that they want to also, learn how to learn software skills, how to teach, because they foresee that this is also something that's useful for them in the long run. But I have not heard that somebody's research has suffered because this is purely on voluntary basis, but we also, of course, encourage them. So I think this feeling of contribution has been increasing over time. So I am very positive about that.
Maybe I can also say from my experience, to give a very concrete number, I would say that I would estimate 25% of my time would be a realistic estimate, which is, that's a large fraction, like 1.5 days a week or so. But one thing that Sudhir said is that the topics where I spend most of that time is developing new content of training materials, and that can be done in a way that aligns with what I will need to learn anyways for the actual things that I'm doing in my focused research project. For someone to lead this group, I think, or contribute to this actively, I think a quarter of their time as an educator would be sort of like an upper limit of what's necessary.
So, Markus, if you allow me, I want to say one more thing. And
please.
So, unless somebody has a question, please feel free to interrupt. One thing I wanted to mention was that I think Markus asked outreach in the beginning, but I think outreach can have different connotations. To me, as NSF-funded PI, outreach means how can I involve the community motivate the community into STEM fields. So the IRSF component of let's say HSF, it has outreach activities also that we do, and we have been preparing a lot of material and have done a lot of outreach. And the next outreach event I have planned is about machine learning here in Puerto Rico. So we have a big focus on that also. And we're also partnering with QuarkNet to organize some sort of data camps where we can teach the importance of software to the high school and to that community, besides the excitement about high energy physics itself. So I just wanted to mention that, if that's also an outreach, I guess, big component.
Thank you. So let me go to the, it's really great to see that there is an active, successful training program going on. And given that we started this for EIC software, knowing how much work this is really great what you are doing and at what scale you are doing this, and that you have a full program with your wish list. So this is really great. Let me go to the last presentation, and we want to share some thoughts, and this is just for discussion, about a community forum for nuclear physics. So also coming back to future trends in nuclear physics computing, which I mentioned at the beginning of today's roundtable, there was a consensus on starting a new community forum. The idea there is to discuss common projects, the role of data centers, so the interplay of those who provide the data center and those who use it, and of course unique challenges of the field. So the possible goals there was to inform the community to how to build successful scientific software projects, taking the unique challenges of the field into consideration, foster collaborative software projects in nuclear physics, and also promote scientific software career support, so to promote those who really focus in their career on software aspects. And during the workshop and also afterwards, there was quite some discussion about how this should be connected with the HEP Software Foundation. It was clear from the discussion that this connection is wished for, and this is, for instance, now also manifested itself that today we had quite some in-depth presentations of our new partner in the Software and Computing Roundtable, DHSF. But how this should exactly look like is a little bit unclear. So how to make this a little bit more concrete? Well, we need a name. The maybe not too creative name which we came up so far is Nuclear Physics Software Forum. What is an easy way to set up a discussion forum is set up a Google group. The HEP Software Foundation has already a Google infrastructure. So instead of duplicating the effort, there is the idea to ask the HEP Software Foundation if we could make this part of their mission, so it would be a new activity. But this, of course, has not been discussed in any detail. The advantages here would be this would really then encourage, instead of, let's say, nuclear physics starts its own frameworks working group or tracking working group, reconstruction working group, to really align this with the existing working groups. In particular, from what we heard today about PyHEP and training, there's a lot of overlap. Regardless what we do, we need some kind of mission statement, and we put some aspects here, which is a little bit more in detail what I wrote here about building how to build successful scientific software projects, really emphasize on common software projects, how we as a community can work better together and promote careers in scientific software. I don't want to go over all of these details because I would like to get some feedback from you. What do you think about getting started with this forum, having this mainly as at the beginning as a discussion forum, but really align this with the HEP Software Foundation? So ask them formally if they would welcome this step, and then really also have our discussion forum where we discuss, but combine this with the ongoing activities in other working groups to really work closer together between HEP and NP. I leave it here, and I really would like to get some feedback, some comments. And please just speak up, because as I have right now my screen full screen, I cannot see anyone raising hands or something.
Well, I do think it makes a lot of sense for us to participate and to try to merge in as much as possible into the existing working groups that are in there. It is always a kind of a challenge to get people to peel off a few more of their cycles to go participate in yet another group somewhere else. But I think that the payoff is potentially very, very large on this. So I'll just second your statement there.
So Markus and everyone, one thing I would say from training aspect is that for example, if nuclear physics, let's say you develop some sort of training that, let's say on GIAN, right? And that would be useful for us, for HEP also, then anybody can use that training and use in their own domain, in their own flavor. So I think that kind of, so nothing should prevent oneself to be the part of a bigger, goal here, because you can always have your own flavor, and that is the way we want people to work. In fact, some of our basic trainings of software can be used by any university. You can just clone and then use it and just give some credit, and that's it. So, yeah.
Thanks. Yeah, no, that makes a lot of sense.
This is Michel from HSF. I think this is way up to you to discuss this in detail and decide what you want to do. But from your last slides, Markus, I think there is quite a lot of overlap with what we are doing in HSF, and I have the feeling that if we manage to find a way where your activity is basically strongly connected to HSF, it will be more efficient for everybody, rather than probably duplicating some of the activities that are basically in common between us. After that, I understand that if you decide that this is the way to go, it is also a challenge for HSF to try to understand how we must evolve our way of working so that there is really, let's say, a nuclear physics activity that is that has its own, let's say, own autonomy and really exists by itself, not only as a kind of working group or things like that. So, but at least from my side on the HSF, I am pretty sure that if you decide to go that, it will be probably more efficient to try to work together and find a way where both you can exist as a nuclear physics software forum and also try to share as much as possible with what we are doing for the things that are, let's say, more neutral, more agnostic in terms of community. I think it will be very nice.
Yeah, I appreciate this comment, and everything what you said also reflects what I try to express here with these slides. I think that some don't like the word synergy, but I think there could be a lot of synergy between HEP and nuclear physics too, that this really becomes something which is beneficial for both sides.
And in particular, I think you should not underestimate the amount of work it is to have, let's say, a decent website, an organization that works in terms of sharing packages, GitHub things, having communication channels that are, let's say, efficient, and it means that there are not too many of them that everything is splitted. So I think in this sense, really, again, but I already told it in the workshop, so it's not new on my side, but I really think that it's really you people from this community to decide what you want to do. But on my side, I would be very happy to help HSF to welcome you if you decide that we should join the effort. And clearly, if you decide this, what I want to say also on the HSF side, we are clear that it means that we have also to change a few things in the way we are doing our work.
Thank you. More comments or questions?
Markus, I have a question maybe for you and for David, other members of the JLab computing planning side. Are there domain-specific problems, challenges, or commonly used packages that just don't overlap enough with the HSF projects that it would make sense for us to go to the extra effort of creating our own?
Well, that's a good question, but I think you probably know the answer to that just as well as anybody else, given your involvement in there. I think that there certainly are some things that make nuclear physics a little bit unique compared to high energy. Some things we can't just take and use right out of the box, and some things are kind of sledgehammers for our thumbtack in our case. That maybe makes it more effort to kind of wield that large weapon than what we need. But I off the top of my head, I can't particularly say of something that has to be developed in nuclear physics because nobody else is going to use it somewhere else.
That to me would be sort of developing a case study for 2 or 3 of those areas would be a convincing case for why the effort should go into creating a subgroup.
So this was part of the discussion of future trends in nuclear physics computing. We asked what is unique about nuclear physics computing, and to what extent is this different? Because there is a lot of overlap, and also nuclear physics is starting to use a lot of the very successful common software projects from HEP. An example for that is, for instance, where we looked at the workshop is ACTS. The differences are coming, and this was the comment Andrea Brazan made earlier in the discussion about how analysis is done. In HEP, in let's say one extreme example, one just cycles over all of the data and looks for an event with a very specific topology. If found, that would be sign for physics beyond the standard model, but otherwise this data is not any more of interest and one can go to the next event. Whereas in nuclear physics, thinking about hadron tomography, one really would like to take all of the data into consideration and look at and find some correlations in that data which are quite strongly coupled. And strongly coupled is also a hint for another difference. HEP is typically more focused on non-perturbative QCD, whereas on perturbative QCD, whereas nuclear physics is looking in understanding better non-perturbative QCD. So there are some differences, and this is the motivation about having a discussion forum where these differences could be highlighted. But there is a lot of overlap in software and in discussions, and it's anyway already happening. So point out another project which is used more and more is Jana 2 by David. He already gave a presentation in one of the HSF frameworks meetings about that. So I think by working commonly together, I think we can also bring what we do in nuclear physics more in in the focus. Another example, for instance, are event generators. A lot of the work in event generators happened for LHC. Something like matching and merging is nowadays standard. That goes back to also what Graeme showed earlier about the accuracy and precision work which has been done by the community. But now, speaking about EIC, these generators need to be upgraded, extended to also fold in observables which are of interest in nuclear physics, which then have some spin dependency, for instance. But the question is, does this need to be standalone, or would this make perfect sense to do this to do this commonly? And I think here at this point we are collecting opinions. And thank you very much for this very good question.
So I'd like to express an opinion. I think you're concentrating on the LHC portion of HEP here, and I'd like to just put in a plug for the neutrino program. I'm also, I mean, I'm here mostly with my HSF hat, but of course I am a Fermilab employee, and I've been very much involved with the neutrino program here. You know, it's pretty clear that our physics is going in this and is going more towards the nuclear side, right? Because in order to understand neutrino interactions, we have to understand how it interacts with the nucleus, and we just don't know enough of the structure of the nucleus and the multi-particle dynamics that go into that to understand the neutrino physics. So, you know, because there's a lot of synergy in the physics we're trying to do here, I think that there could also be related synergies with the tools, the software tools. And so I think it does make sense. I would put in a plug to try to err on the side of more collaboration here. You know, I remember reviewing JLab long ago, and was surprised to find out you kind of had your own branch of Pythia. I don't know if that situation has changed in the past 5 years, but that's an obvious point of contact where both sides would really benefit from greater collaboration. And we are collaborating already. I just approved a test beam experiment from experimenter at JLab at the Fermilab test beam. So I just think that that if it's not too much overhead to work cooperatively together, it could provide a lot of benefit. Just a point of fact, the HSF Google groups are not really extremely noisy lists in any sense. So I think adding in the nuclear physics community to that Google group infrastructure would not be a minus. I think nobody's inboxes are going to be filling up because of this, and I think it might actually be a plus with greater communication between us. So.
Thank you very much for this great comment. Yes, I did in no way want to leave out the neutrino community. I was just giving one example, and yes, that there is a lot of overlap there. In particular, what now speaking with my Jefferson Lab hat on, what things which are happening at Jefferson Lab, how this could be relevant for the neutrino program. There is no, regarding your short question about Pythia, there is no standardized answer to that. There exists some unique flavors, but also there is a active collaboration with the Pythia collaboration to get a lot of these modern QCD effects into the Pythia 8.3.
Oh, that's good. Yeah.
And we started with that with 8.1. So, but let's not get into lost in any
no,
details.
I didn't want the details, but that's good to know that that situation is changing. Thank you.
Yeah, but this is for that. It's really, but this is an excellent example for working together and doing common things, and instead of creating starting from a common ground and then creating some own flavors, but not fragmenting. Great comment, thank you. Any more comments? Let me thank the speakers, Graeme, Eduardo, and Sudhir for really very great presentations. Thank you very much. This was very interesting. Even so, I was already a little bit familiar with what you are doing. I really learned a lot from these presentations, and it was really great that you pointed out places where we can work together, where we can cooperate. And thank you very much for the feedback on the discussion. We continue then the roundtable in February, and the topic will be I/O for the future. Thank you very much.